Hi everyone. In this video, we are going to look at a calculation example of an ideal air standard Brayton cycle. I'm going to show you how to systematically identify, formulate, and solve the problem by using what you have learned earlier. Now, let's have a look at an example of an ideal gas turbine cycle. In the first sentence, the ideal air standard Brayton cycle operates with air entering the compressor at 95 kPa, 22 degrees Celsius. The first information that we have is ideal air standard Brayton cycle. It means that we have a cycle consisting of two isentropic and two isobaric processes. From the same sentence, we have the compressor inlet conditions at point 1. So we have P1 equal to 95 kPa and T1 equal to 22 degrees Celsius. Next, the pressure ratio RP is 6.1. It means that P2 over P1 is 6 in the compressor and equals to P3 over P4 in the turbine due to two isobaric processes. Next, the air leaves the heat addition process at 1100 Kelvin. It means that the temperature of air leaving the combustion chamber at point 3 or T3 is 1100 Kelvin. We want to determine the compressor work and the turbine work per unit mass, the cycle efficiency, the back work ratio, which I'm going to describe the definition of this parameter later on, and finally compare the compressor exit temperature T2 and the turbine exit temperature T4. Lastly, constant properties are assumed, which means that Cp and K of air at 25 degrees Celsius are used throughout the solution. Now, having extracted some important information from the problem statement, let's start by identifying the problem. Typically, engineering problems can be solved systematically by making sketches of engineering diagrams such as process flow diagram or PFD or graph. In this example, we can identify the problem by sketching a thermodynamics diagram in order to understand the overall system. We can then identify what we need to know and apply relevant fundamentals to solve the problem. Here, we use a TS diagram. We have an ideal air standard Brayton cycle, which consists of two isobaric and two isentropic processes as shown. In two isentropic processes, we require compressor work in process 1-2 and obtain turbine work from process 3-4. In two isobaric processes, we need to supply heat in process 2-3 and to reject heat from process 4-1. At point 1, we have already known the pressure and temperature conditions. Now, at point 2, which is the compressor exit, we know only the pressure, which is 6 times the compressor inlet pressure. But we don't know the exit temperature or T2 here. At point 3, which is the combustion chamber outlet, we know both pressure and temperature. And lastly, at point 4, we know only the pressure. From the problem statement, we need to determine the cycle efficiency, the back work ratio, and to compare T2 and T4. You can see the information in green represent the input or known variables, while the information in red represent unknown variables or the parameters we want to determine. We have to develop some equations such as mass and energy balances or thermodynamics relationship, which relate between our input and known variable or known variable and the unknown that we want to determine. We have to start from the point which is fully defined, such as point 1 or point 3, where we know both temperature and pressure, and try to complete the other state unknown, which are T2 and T4 in this case. After that, the heat and workflow involved in each process step can be determined by mass and energy balances. Finally, we can then evaluate the performance of the cycle we are considering. You can see that we have completely identified our problem. We know what we want to determine. Now we have to figure out how to get the result from what we have and what we have learned so far. However, the calculation steps might not be clearly outlined. Therefore, by using a simple chart called solution map, we can clearly formulate our solution procedure and then effectively solve the problem. First, we have to classify our parameters into different groups, which are input data, unknown parameters, heat and work variables, and performance indices. Here, we have 6 input data that we have already known their values. They are T1, P1, P2, T3, P4, P3, and P4. 2 intermediate state parameters that we don't yet know are T2 and T4. The heat and work variables to be determined are WCOM and W turbine. Finally, 2 performance indicators, which are Brayton efficiency and the back work ratio, are to be determined. Next, we start to establish relevant relationships between variables, starting from the parameters in the outer layer, which are the performance indicators. The Brayton efficiency could be determined from the definition of what we get over what we give, which is the net work output divided by the heat input. Here we have the equation as shown in the first yellow box here. To calculate the Brayton efficiency, apart from WCOM and W turbine that we need, we also require Q in. So, we list Q in as another heat or work variables to be determined as well. Next, the back work ratio can be determined from the definition of work input divided by work output. That would be WCOM divided by W turbine. We can now move on to the next layer to determine the heat and work variables. The compressor work can be determined from the mass and energy balances of process 1-2. To achieve what we want, we need T1, T2, and CP. However, we don't know T2 at this point. The turbine work can be determined from the mass and energy balances of process 3-4. Similar to process 1-2, we need T3, T4, and CP. However, we don't know T4 at this point. Finally, the heat input can be determined from the mass and energy balances of process 2-3. We need T2, T3, and Cp. We can see that at this stage, we have only T2 and T4 left to be determined. Should we know these two values, the solution procedure will be completed. We can get T2 and T4 from isentropic relationships of process 1-2 and process 3-4, respectively. We have now completely formulated our solution procedure. The calculation sequence can then be followed from left to right. Now, to start solving our problem, first of all, we start with the calculation of T2 from the isentropic relationship of process 1-2. By using the isentropic relationship between the temperature ratio and the pressure ratio, we can substitute all known parameters, which are T1, P1, and P2, into the equation to determine T2. And we get T2 at 492.5 Kelvin. To use this equation, you have to be very careful about the temperature and pressure units, since this equation is a thermodynamics relationship. They must be in absolute temperature, for example, Kelvin or Rankine, and absolute pressure, which include atmospheric pressure. Similarly, T4 can be calculated from the isentropic relationship of process 3-4. We can substitute all known parameters, which are T3, P3, and P4, into the equation to determine T4. We get T4 at 659.1 Kelvin here. After having determined T2 and T4, we can apply mass and energy balances in process 1-2, 3-4, and 2-3 to determine WCOM, W turbine, and Qin respectively. First of all here, considering mass and energy balances around process 1-2, which is a compressor. The energy balance and mass balance around the compressor can be written as shown. Since we have only one inlet and one outlet in this process, M1 dot is equal to M2 dot and simply written as M dot. Combining mass and energy balance equations, we have WCOM equal to M dot multiplied by H2 minus H1. For gas, enthalpy change between two states can be calculated from Cp multiplied by delta T. Finally, we have the specific compressor work as Cp multiplied by T2 minus T1. Substituting all known values, we have WCOM at 198.15 kilojoule per kilogram. In process 3-4, we can do mass and energy balances as done in the process 1-2. Combining mass and energy balance equations yield the specific turbine work, or W turbine, as Cp multiplied by T3 minus T4. Substituting all known values, we have W turbine around 442.5 kilojoule per kilogram. In the last energy balance, process 2-3 requires heat supply. From the mass and energy balances, we obtain Qin as Cp multiplied by T3 minus T2. After substituting all known values, we have Qin around 659.1 and 9.6 kJ per kilogram. Next, we can calculate the thermal efficiency of the cycle. The net work done is W turbine minus W compressor, which is around 244.3 kJ per kilogram. The cycle efficiency calculated from W net over Q in becomes around 40%. Next, the back work ratio is defined as the ratio between W in over W out. In this case, that would be W com over W turbine, which we can calculate it to be 0.448. It means that for 100% of work generated by the turbine, around 45% will be used to drive the compressor, and the remaining 55% will be useful work to drive the generator. Any cycle with low back work ratio will be an efficient cycle. Lastly, comparing T2 and T4, we can see that T4, which is the turbine exit temperature, is higher than T2, which is the compressor exit temperature. It means that we can use the turbine exhaust gas to heat up the compressed air before entering the combustion chamber. This recovered heat can help reduce the fuel consumption in the combustion chamber. Q in will be reduced, thereby increasing the thermal efficiency of the cycle. We'll take a look into the detail of this heat recovery scheme in the upcoming videos in this series. Now, that's it for this example. Thank you for watching. Goodbye.